Good evening, friends. My name is Pankaj Dunka. Today, our topic of discussion will be on first law when we apply that to a when we apply that to a closed system. Now, we know that when a system interacts with its surrounding, so it can interact in two modes, either in the form of heat or in the form of work. We know that these both work and heat, they are path function and they are energy in transit. Now consider a very classic example. And this experiment was done long time back by Joule. What he did, he inserted a churner and with the help of these weights, what will happen as these weights will fall down, this churner will start rotating. And in this chamber, there is some fluid, let us say known fluid, let us say water. So what will happen as these weights will fall down, the mechanical energy will get transformed into internal energy. But right now we don't know anything about internal energy. So what he did, he insulated this whole chamber and inserted a thermometer here. So after some time of churning, he noticed that the temperature of this thermometer has increased. And we know that heat is the only form of energy which comes into picture whenever there is a temperature difference. But what he did, he does some amount of work on this fluid which is a closed system. Then he removed this partition, and what will happen as the partition is removed now, the heat because of temperature difference will move out to atmosphere, and the temperature of this thermometer will again come back to its original limit. So what he did basically, he performed a process. He performed a process in one direction and another process in the same direction so that he can arrive at the same point. So he performed a cycle. And in this cycle, he observed that the amount of work which he did in this cycle is proportional to the amount of heat he rejected from this cycle. Or in other terms, the total amount of work is proportional to total amount of heat. But in those days, heat and work were not in same units as we consider them as Joule. In previous days, in primitive days, people used to talk of caloric theory of heat, so calories. So this cyclic work will be equal to cyclic heat transfer, but with a proportionality constant, which is known as Joule's equivalent or the mechanical equivalent of heat. But when we talk of SI units, then what will happen, this J will be 1, that is joule, kilojoule. So this is the general law of nature, and which we know as first law. And we look this law in these days as the net amount of heat transferred in a cycle is equal to the net amount of work done in that particular cycle. This is the first law of thermodynamics, that is the energy conservation. That is, if energy in one form disappears, then equivalent energy in some other form has to appear. That is, the energy is conserved, conservation of energy. Or in differential form, dW is equal to dQ for a cycle. Now what will happen? If instead of a process, instead of a cycle, I am talking of a process. That is, a system is performing a process, that is moving from 1 to state 2. Then if moving from 1 to state 2, let us say I give this system some amount of heat, and in turn this system develops some amount of work. Then when I subtract this heat from work, I will observe that there is something which this system stores. With the amount, some amount of energy is left with the system, and that energy is known as stored energy or system's energy or energy of the system simply. So in differential form, I can write that dq minus dw, as these are path functions, so d cut is equal to de, or dq is equal to de plus dw. So when we talk of a process, the first law of thermodynamics will be given by dq is equal to de plus dw, where this de stands for energy stored by this particular system. Remember one thing, system can never store heat, it can never store work, because these are energy in transit. That is, these energies comes into picture whenever system interacts with its surrounding. But what is this dE? This is the amount of energy stored by that particular system. So let us discuss in what forms a system can store energy. Now the modes of energy storage by system. Number one is the macroscopic. What do we mean by this macroscopic term? Macroscopic means macroscopic kinetic energy or macroscopic potential energy. So if a system is possessing some velocity v, then this will be what? mv square by 2, where v is the velocity. And if that particular system is at certain height, that is, let us say z, then this will be the amount of potential energy stored by that particular system. Now, the second mode of energy storage is microscopic. Now, microscopic means that energy which is stored in molecular and atomic structure of that particular system. Now, it can be translational, it can be vibrational, it can be nuclear, and the energy of that particular molecule as well, that is we know as internal energy. So if we neglect every other energy, that is translational, vibrational, molecular, electric, chemical, any energy, then this is the only energy which is left in that particular thing which we know as internal energy. So the total amount of energy which a system can store is the macroscopic kinetic energy, macroscopic potential energy, plus microscopic, this internal energy. If we can neglect this, how? If the velocity level, if the velocities of that system is very small and the datum difference is very small, then we can neglect it. Then the energy stored by the system is nothing but the internal energy of that particular system. And later on, we will come to know that this internal energy is a function of temperature for an ideal gas. So now, if I am interested in writing the first law of thermodynamics for a closed system performing a process, then that can be written as dE plus dW is equal to dQ, or du plus dW is equal to dQ. In differential form, in absolute sense, from 1 to 2, it is Q1 to 2 is delta E plus W1 to 2, or Q1 to 2 is delta U plus W1 to 2. Now friends, now the question is, you can see that I am not writing delta W or delta Q because I know at this moment of time that these are path function, these are not point function. But what about this delta E? I am writing this delta E means this has to be a point function. So let us see that this is a point function. How? How can we prove that this is a point function? Consider a PV plane and consider some processes performed by this system. Let us say that the system is moving from 1 to 2 along path A and it is returning back from path B, and there is alternate path C from which this system can return to original state 1. Now, if I write first law of thermodynamics for path A, then I can write that heat transfer in this path is equal to change in energy for the path A plus work done in path A. If I write for this path B, then I can write for path B is equal to delta E for path B plus W for path B. Similarly, Q for path C will be delta E for path C plus W for path C. Okay. Now consider any cycle. Consider cycle 1A to B. That is 1 from A moving to 2 and then from B back to 1. Then for this cycle, I can write what? QA plus QB, that is net heat interaction, which is equal to WA plus WB. Why? Because for a cyclic process, the first law says that sigma Q is equal to sigma W. Now from here I can say that QA minus WA will be minus QB minus WB, just rearranging the terms. So what is QA minus WA? If I look here, QA minus WA is delta EA. And what is QB minus WB? It is minus delta EB. So this is, let us say, my equation 1. Now if I consider the second, if I consider that instead of path B, the system is coming back from path C. That is, I am talking of 1A to C1. Then I can write first law is net heat transfer, that is QA plus QC is equal to net work done, that is WA plus WC. So I can write QA minus WA is equal to minus QC minus WC. Now, what is QA minus WA? It is delta EA. What is QB minus QC minus WC? It is delta EC. So let us say this is equation 2. So compare equation 1 and 2. You will get that delta EB will be same as delta EC. Means what? The change in energy from 2 to 1 along path B is same as change in energy from 2 to 1 along path C. Hence, this E is a point function. That is, it is independent of path performed by a system. Hence, E is a property of a system. Now, we know that E, that is the total energy stored by a system, if we neglect the macroscopic energies, is nothing but the internal energy of that particular system. Hence, U, that is the internal energy of a certain system, is also a property of a system. Now from here, with this property, we define a term known as specific heat at constant volume. And how we define this specific heat at constant volume? Specific heat at constant volume is defined as the rate of change of internal energy with respect to temperature keeping volume constant. So this is the way in which we define specific heat at constant volume. So for a constant volume process, what I can write here is delta U for a constant volume process will be integral. This will come here. It is CV delta T from any limits from 1 to 2, like this. Now if you write your first law of thermodynamics for a closed system, you will say that dq is equal to du plus dw. And if this system is performing displacement work, so I can write this. So if the volume is constant, then this pdv term will go. So this dq will simply be du, or q1 to 2 will simply be u2 minus u1, or I can write this as integral 1 to 2 cv dt. So heat transfer in a constant volume process is nothing but the change in internal energy. So one will be tempted to find out the specific heat at constant volume if we compare this like this, that is, it is heat transfer at constant volume to that of temperature, absolute temperature. But this way of defining specific heat is not true. Why? Now we know that specific heat is a property, and and temperature is also a property. But this justification of Cv as a property is not going by considering Q, because Q is a path function, it is not a point function. Hence, the best way to define specific heat at constant volume is with respect to internal energy. Now, we know enthalpy. We define a new term, enthalpy, and this enthalpy is internal energy plus PV, and we know PV is flow work. So this is another way of representing energy, that is energy when coupled with motion. Now you consider your first law of thermodynamics, that is dq is equal to du plus pdv. Friends, if you differentiate this, you will get dH is equal to du plus pdv plus vdp. And what is this? It is dq. So you can write this dH as equal to dq plus vdp, or simply dq as equal to dH minus vdp. So if you consider a process where pressure is constant, then this heat transfer at constant pressure will be equal to what? The change in enthalpy, simply. So here we define a new term, that is specific heat at constant pressure, which is defined as the rate of change of enthalpy with respect to temperature when pressure is held constant. So the total change in enthalpy will be nothing but integration of this term Cp dt from 1 to 2. Another important thing, then as delta H is nothing but heat transfer in that particular process, that is Q1 to 2 is delta H, which is 1 to 2 Cp dt. So one will be tempted to write again Cp as what? Del Q by del T at constant pressure. But again we know that Cp is a property of that particular substance. So this property is defined with respect to a non-property, that is a path function, which is heat transfer. Hence it is wrong to define specific heat in this term. Hence the correct way of defining specific heat at constant pressure is with respect to enthalpy, which is a property. Now you have heard that first law of thermodynamics is also the law of conservation of energy, that energy of an isolated system remains constant. That means energy can neither be created nor be destroyed. So to conceive this idea, again come back to the first law of thermodynamics for a closed system. Now what is an isolated system? Isolated system is that system in which the identity of mass remains fixed. That means no mass can cross its boundary, mass interaction is not there. At the same time, no energy can cross its boundary, no energy interaction. That means no heat interaction, no work interaction is there. So if this is the case, then heat interaction for this isolated system as well as work interaction for this isolated system will be constant. So the change in internal energy for this particular system will be zero, or internal energy for this particular system is a constant. Or in general, energy of this particular system, stored energy, is a constant. Hence, for an isolated system, energy can neither be created nor be destroyed. It can only be transformed. Hence, this is the concept of universal entropy constancy. But remember one thing, I am adding one more thing to this statement. What that thing is? In my eyes, what I view first law is that energy can neither be created nor be destroyed. It can only be transformed. But this is quantitative description. That means quantity-wise energy can neither be created nor be destroyed. The quantity-wise energy of a isolated system remains constant. But what will happen, we will look later on when we talk of second law of thermodynamics, because energy is conserved quantity-wise, but quality-wise it always degrades. So at last, we will be finishing this topic of first law of thermodynamics for a closed system with this machine, PMM1, that is perpetual motion machine of first kind. What is this machine? It is a machine, let us say an engine which will continuously develop work, which will give you the work, but consumes no energy in the form of heat, or consumes nothing. So it is a machine which will continuously give you work, or it is a machine which will be continuously absorbing work and in turn giving us nothing. That means this is the plain violation of first law of thermodynamics. How? Energy in one form is appearing, but no another form of energy is disappearing. Here, energy in one form is disappearing, but no other form, energy in other form is appearing. So this is the violation of first law of thermodynamics, and if any machine violates this first law of thermodynamics, so that machine will be called as perpetual motion machine of first kind. So thank you very much for your patient hearing. If you like my video, then please do subscribe.